In this video, we're going to look at another limit at infinity. When we first look at this question, we think to ourselves, we're not dealing with a limit at infinity, we're dealing with a limit as t approaches 0 from the right, which you'd be correct at face value. But if we dig a little deeper, which is what our first step of this whole process is going to be, we're going to find that we're actually dealing with something of a limit at infinity. Okay? Because what we've been doing these past two problems that we've done is we've been able to substitute a different variable in for an expression that's in our function originally. The past two times we've been doing it simply because it's a shorthand notation that helps us more easily recognize what we're dealing with. But here in this case, it'll actually help us to see better what we're evaluating and to appreciate that this is a limit at infinity. So in order to see that this is actually a limit at infinity, let's go ahead and make another one of those substitutions that we've been doing the past two problems. Okay, so the first thing we're going to do, wow, that didn't load. Let me redo that. There we go. First, let x equal 1 over t. Let's just stick to the pattern of making x's and t's our prevalent use of variables in these limits here. And we're going to note that as t approaches 0 from the right, which was given to us in our question, we're going to see that as t gets arbitrarily close to 0 from the right direction, this denominator of our x, what we've let be known as this fraction, is this denominator is going to get very, 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 very small. Right? It's going to keep decreasing as we approach 0 from the right. But when our denominator gets very small, that means our number as a whole, like this 1 over that very small thing, is actually in turn going to get arbitrarily large and grow towards infinity. So as t grows closer and closer to 0 from the right, x is going to approach infinity. This is where the limit at infinity comes in, because now we're going to go through the substitution of taking these x's 1 over t's and translating our limit into a limit at infinity. So let's go ahead and do that. So we have the limit as t approaches 0 from the right. We're just going to rewrite what we had originally. Tangent inverse of 1 over t is equivalent to saying by the substitution that we have above is tangent inverse of x. And instead of t approaching 0 from the right, x is going to approach infinity. X is going to approach infinity. Let me clarify that. Okay, so now we're dealing with this. And to more readily see what this limit will be, we want to figure out what happens to tangent inverse, what values does it return as x grows arbitrarily large. And in order to do that, I've pulled up right here the graph of tangent inverse just to kind of jog our memory. It's not one that we see every day, but this is tangent inverse. And we remember through various rules of taking inverses of functions, we have to restrict the domain down to make sure that it's a one-to-one function, and then once we do that, we arrive at this type of graph here. Okay? And we see that as x's, or in this case, yeah, our x's, go arbitrarily large and get close and get larger and larger arbitrarily here, our tangent inverse function never really breaks pi over 2. It's constantly approaching pi over 2, but it never fully becomes pi over 2, if that makes sense. So tangent inverse of infinity is not really a value that we can take, but we know that as x approaches infinity, tangent inverse will approach pi over 2. So with that being said, we scroll back up to what we have, and we see that as x approaches infinity here, tangent inverse of x, the limit of that will be pi over 2, because that's the value that tangent inverse approaches as x grows arbitrarily larger and larger.